In Chapter 11, we'll talk about the chi-square distribution. By the end of this chapter, a student should be able to interpret the chi-square distribution as the sample size changes. And we'll see that as the sample size changes, so does the degrees of freedom that is associated with the distribution. Now, there's a lot of different tests that go on with the chi-square distribution. In fact, there's 4 of them. There's the test for the single variance, the goodness of fit, the test of independence, and the test of homogeneity. Let's look at those in a little bit more detail to summarize them. In the single variance test, what we will be doing is we're going to test the variability of a single random variable, hence the name single variance. So we could answer questions like, does a soap dispenser dispense approximately the same amount of soap each time? In the goodness of fit test, we're going to determine how well a given data set fits a distribution, hence how good does it fit. We could ask questions like, are lottery numbers uniformly distributed, or is it that some numbers occur more frequently than others? We could look at the test of independence. This would determine, this one's interesting because it's specifically about categorical variables, and we're going to determine if categorical variables are independent. So for example, we could ask questions like, is a person's preference in ice cream flavors affected by their age? Then lastly, there's the test of homogeneity. We'll look at 2 populations and ask, do these have the same distribution? So we could ask a question like, do families and single-member households have the same distribution of automobile types? So in section 11.1, we're just getting an introduction to the chi-square distribution. There are some requirements to use this, though. Again, we will always need a simple random sample. And here, the population must be normally distributed, even if the sample size is large. This one's very sensitive to discrepancies. So large discrepancies from the normal distribution mean that this will lead to large errors in our calculation, and that needs to be avoided. So in this distribution, the population must be normally distributed. And specifically what the chi-square distribution is doing is it's looking at the standard deviation and or variance of a random variable. The test statistic is chi-squared. It's the Greek letter x, which is chi. So chi-squared is n minus 1, the number of the sample size, minus 1 times s squared divided by sigma squared. In this course, we'll be using that the degrees of freedom associated with with the chi-square distribution will be n minus 1. As you move on to other textbooks, you may see, and in other courses, that there are other ways to calculate the degrees of freedom for this distribution, but for this course, we'll use n minus 1. And we will say that our random variable x follows a chi-squared distribution, and then we could list the degrees of freedom. So say there was 6 degrees of freedom, then we would say our random variable x, so you may even want to like put capital letters here, I don't know how, just to distinguish it, that our random variable x follows the chi-squared distribution with degrees of freedom 6. So as this sample size changes, so will the graphs of the chi-square distribution. Notice this, the chi-square distribution is not symmetric. We no longer have a bell-shaped curve that's symmetric about the mean. Okay. Also notice that the values of the chi-square cannot be negative. They only go from 0 to positive up until infinity, theoretically positive values. Now, we'll calculate this from a table. And when you're using the table, you want to look to the right of the critical value. So what would that mean? So if you come down here and look at our graph, you will see that this portion of it's shaded. This is chi-squared. This is our critical value. So when we look at the table, we need to make sure that we're looking for area to the right when we're looking for our critical values. But what is interesting is if you look over here, as the degrees of freedom increase, so this is our degrees of freedom of 1, and here's the shape of the curve when the degrees of freedom are 5, and here's 10, etc., etc., etc. As the degrees of these freedom increase, the distribution does become more symmetric, but in general, we should not expect that it should be symmetric. Okay, so let's practice finding critical values with our table. So let's come down here, and let's say that we are looking for, let's say our data set has degrees of freedom 6, and that we're looking for a confidence or an alpha level of 10%. So our confidence level is 90%. And let's find both left and right hand. So if we're looking for the middle 90% of the data, then I would have 5% of the data left over here and 5% of the data left over here. So if we were looking for, let's start with chi-squared on the right, this right hand critical value, we would come up to our table. The area to the right is going to be 5%. So we come up and find the 5% category, which is here. And then we come down to where our degrees of freedom are, which is 6. And where these two meet, 12.592. This is our right hand critical value. So 12.592. So this corresponds to chi-squared, and then we just put the 0.05 here. That's from the table. That's not the degrees of freedom. Okay. Now, if we're looking for the left-hand one, now the area to the right of this critical value, this means we're looking for the chi-squared, and we want 95% of the data there, because that will be on the right-hand side. Let's find the value that corresponds to that. So we come back up, and we find chi-squared 0.95, which is here. Again, come down to 6 degrees of freedom. That critical value is 1.635. So those are our two critical values. If the degrees of freedom is 6 and we have an alpha of 0.10. Right? So let's try another one. Let's try, let's say the degrees of freedom are 11, and that our alpha is equal to our common 0.5. That means our confidence level inside of here would be 95%. So we'd have 5% to split among the two tails, so this would be 0.025, and over here as well, 0.025. So again, on the right, now the area to the right would correspond to, this is chi-squared 0.025. That's what I'm going to look for up in the table. So we come back up here, chi-squared 0.025. Our degrees of freedom are 11. So we come down here and we see that that critical value is 21.92. May as well bring along the 0 to keep everything in 3 decimal places. All right, so we just have to find the left critical value. So now we have to figure out how much is in between, or to the right of this. This corresponds to, on our table, chi-squared 0.975. So we come up here looking for that. 0.975 falls here. Again, come down for 11 degrees of freedom, and we should get 3.816. So the left hand, 3.816. The left hand critical value for this region is 3.816.